Hi everyone. Today we are going to see the linear feedback shift register by using Verilog language for the application of random bit generation and random number generation. See, linear feedback shift register in computing LFSR is a shift register whose input bit is a linear function of its previous state. The most commonly used LFSR is exclusive OR, simple exclusive OR, or else we can say as a XOR gate implementation. See, this is the two input. The output has to be inserted as a first bit. Then the first bit has to be shifted to the next bit. So in this way, this output has to be inserted here and the output going here. This is the random bit. Here the output may be 0, 1 and like that it will come. Okay, see, this is the first example. In the first clock cycle, the output, the initial seed value will be 1, 1. The output will be going to the as a 0th bit. So the final output will be here the 1 and the next clock cycle again 1. Okay, here this output 1, 0. So the output will be 0. Again this clock cycle output again 1. So likewise the output has been changed. Okay. See, the initial value of the LFSR is called the seed, and because the operation of the register is deterministic, the stream of values produced by the register is completely determined by its current state. Likewise, because the register has a finite number of possible states, it must eventually enter a repeating cycle. However, an LFSR with a well-chosen feedback function can produce a sequence of bits that appears random and has a very long cycle. If you want more long cycle, the number of bits has to be increased. Okay, for the application of LFSRs include generating pseudo-random numbers, pseudo-noise sequences, fast digital counters and whitening sequences. Both hardware and software implementations of LFSRs are common. Okay, here our case we are going to see that 8-bit LFSR and as well as the Verilog simulation also. Okay, in the seed value of all the 8 bits, here it is mentioned inside the square bracket, inside the square 1 0 1 0 1 1 1 0, the hexadecimal value AC. Okay, and the output, the corresponding output may be executing in the first clock cycle. Here this output is 1. The meaning is what? The tapping points are 4, 5, 6 as well as 8. If the number of bits are increased, the tapping points also changed as well as they increased also. Okay, here the 8-bit LFSR tapping points 4, 5, 6 and 8. So after the 3 XOR, this output goes and fed back to the as a first bit. Okay, this bit is the random bit. Then the whole number we can say as a random number. Whole number as a random number. 8-bit actually the maximum value of the 8-bit is all ones. Maximum value all ones. That is 255. So the number, what is the present value after the 255th cycle only, the number only will be repeated. Okay. So see here, the corresponding value I can say x1 is 1, x2 is 1 and x3 is 0. Okay, these x1, x2, x3 also we are going to use in the programming. Okay, in the second clock cycle, see here the tapping points are changed. At the same time, the register values has been shifted to 1 bit. See here previous cycle. So here the 1 is there. Again now it is shifted here. Okay, and the output values x1, x2, x3 all are shifted. Again it goes back and fed back here. Okay, now see, this is the Verilog programming for the LFSR. So one input which must, that is a clock, that is the input. Remaining all are output, x1, x2, x3, random bit, random number, all are outputs. Here random bit as well as random number, both are register. I am declaring as a register because we need those output also. Okay, here it is random number, totally 8 bits. So 7:0 I am mentioning, and the intermediate signals. I am making x1, x2, x3 for register for our convenient. The initial seed value register, that is 8 tick HFF. This H will represent a hexadecimal. FF all are ones, all are binary ones I am specifying. Okay, so this is the concept. Always we have to go for the sequential So passage of clock. So every positive clock edge, this will execute. So x1 is equal to, that is the random is the local signal. See here, this value is the random. Okay. So here this value 5th as well as 7th, because the bits are starting from 0 to 7 or 7 down to 0. So accordingly I have taken this value 5 and 7, 3 and 4 XOR gate, then output also coming here, and this is this curly braces. This is used for the concatenation operator and concatenating, and will give it to this output will be assigned as a random underscore number, and a random bit also. This x3 is the random bit. Okay, end as well as the end model, since we have used begin, so end it must come. Okay, and the end model completed. The simulation output, see here, all the input as well as the output are grouped in the Modelsim software. Okay, the x1, x2, x3 all are grouped, and this is the random bit. The yellow color which is showing these are the bits. See, based upon these values, the output bits also changed as well as represented here. Okay, see, what are the more improvement? If we want more number of randomization, we have to go for more number of bits. Tapping points are different if number of bits are changed. If you want to know the more details, and go for this Wikipedia LFSR, and you can take all the tapping points and for any number of bits, and you can use it for our programming. Okay, significant point. Instead of XOR gate, we can use the XNOR gate also. The initial value of all the bits are important. If you are using XOR gate, the initial value of the all bits should not be 0. If you are using XNOR gate, the initial value of all bits should not be 1. Okay, that's all. The next video we will go for PHDL.